Real-time adaptive audio filtering for auditory stress mitigation in sound-sensitive epileptic individuals. Sounds pretty long, right? Let's explain.
Meet Leo. To us, a busy classroom is just life. But to Leo, the world doesn't just sound loud. It feels overwhelming. For children with severe sensory sensitivities, the everyday environment is a minefield. A dropped pencil, a sudden voice, a slamming door. These aren't just distractions. They are physical jarring strikes that trigger panic, fear, and exhaustion. When the world becomes too much, the medical solutions we offer are heavy. Endless medications that can dull a child's spark, or invasive life-altering paths that carry a heavy weight. It's a heartbreaking, exhausting cycle for any family. In our current technology, it has fallen short. Standard devices might detect a spike in stress or send an alert after a meltdown begins, but detection after the danger hits is not the same as protection before the harm is done. This is why we had to exist. A real-time adaptive noise suppression system that doesn't just passively block the world out. It actively intercepts the triggers. It creates a personalized, calming acoustic shield, neutralizing the threat before it ever reaches Leo, allowing his mind to finally find peace. With this right protection, the classroom is no longer a battlefield. Leo does not have to hide away in clinics or rely on heavy interventions. He can step out into the sun, look his friends in the eye, and just get to be a kid.
Startle epilepsy affects between 4 and 7% of reflex epilepsy patients. Seizures are triggered by everyday sounds, a car horn, a dropped plate, someone clapping. What makes it so difficult to treat is that the trigger isn't inside the brain, it's in the environment. Medications provide only partial relief, and surgery is frequently not an option because the seizure zone sits right at the motor cortex. So we decided to start at the trigger itself, at the acoustic level, before it can start a neurological cascade.
We designed a wearable real-time audio processing system where a microphone captures the surrounding environment continuously and a Raspberry Pi 5 analyzes every audio frame in real time using a signal processing technique called WOLA, Weighted Overlap Add. The moment an acoustic spike is detected, the system suppresses it and delivers the safe filtered audio to the user through the headset. Under normal conditions, the system is completely transparent. You hear everything naturally. It only acts when a dangerous trigger is detected and zero manual intervention is required. It just works in the background.
Here we have the original unprocessed noisy audio signal. As we can see in the top graph, the audio is mostly stable, but there are sudden high amplitude peaks at certain moments. These peaks represent loud impulsive sounds such as a bang or a sudden noise. In this case, it would be the alarm, which is pretty harmful for sound-sensitive ears. In the second graph, we analyze the input RMS energy. The blue dashed line represents our threshold. Whenever the RMS energy crosses this threshold, the system identifies that section as a high-energy noise event that needs mitigation. Our plan is to use short-time fast Fourier transform to visualize and identify the target frequency components of these loud events, while RMS energy helps us detect when the signal becomes too strong. So first, this is the original unprocessed audio before mitigation. Now, this is the processed audio after mitigation. In the top graph, we can see that the sudden peaks from the original signal have been significantly reduced. The system targets only the loud sections that cross the threshold instead of changing the entire audio signal. In the bottom graph, the output RMS energy is shown after processing. We can see the green RMS curve stays mostly below the threshold, which means that the high energy peaks were successfully dampened. This shows that the mitigation process reduced the sharp bang-like noises while keeping the rest of the audio mostly unchanged. Now, I will play the processed audio so we can hear the difference.
Our system runs on a Raspberry Pi 5 with 16 gigs of RAM, fast enough to run everything in real time with under 10 milliseconds of latency. A wireless mic captures the audio at 32-bit precision, so even sudden sounds don't clip. The processed audio then goes straight to the headphones, giving the user a safe filtered environment at all times. Our whole system assembly should stay under 350 grams, light enough for kids to wear all day.
So what makes the system genuinely novel is that there are no commercial noise cancelling products that target specifically impulsive and high-frequency transients. Existing ANC technology is built for sounds like airplane engine hums, not door slams. Our system is built around specifically 8 strict engineering requirements, some of which include under 10 milliseconds of latency, at least 25 decibels of trigger suppression, a speech intelligibility score of above 0.6, and a full 12 hours of battery life.
For patients with refractory startle epilepsy, this device could mean fewer seizures, fewer falls, and more freedom to live a normal life. For children especially, whose development is disrupted by daily seizures, and even a partial reduction in seizure frequency carries enormous long-term benefits.